Hey guys! The powder you can see right now is a chemical element, the noble and precious metal ruthenium. I bought this element to try synthesizing ruthenium tetroxide and isolating this oxide in its pure form, but today we are going to talk about something else. For the experiment I've prepared for you, I'll need just under 1 gram of this element. I also need 15 grams of zinc dust, which will play an important role in this experiment. I place this zinc dust into a quartz tube and heat it thoroughly in a stream of hydrogen, in order to remove as much zinc oxide as possible that formed during storage of this reagent. After that, I mix the cooled and reduced zinc powder with the ruthenium powder in a quartz test tube, and then heat it evenly with a butane torch for several minutes, until it begins to glow a dark red color. Then, after the sintered powder has cooled, I break the test tube and thoroughly grind the material we obtained. Then I transfer the ground powder into a beaker with distilled water, and while stirring, slowly add diluted hydrochloric acid drop by drop. It's very important to do this slowly. Ideally, you should add the acid once a day, and after each portion, let the powder react with it. When this alloy is treated with hydrochloric acid, the ruthenium remains as undissolved residue, and hydrogen is produced during the dissolution process. Ruthenium, like many other platinum group metals, is able to bind hydrogen. A small portion of the hydrogen released during the reaction forms a ruthenium-hydrogen compound. After a couple of days, another added portion of acid still produces small gas bubbles, which means that not all the zinc has dissolved yet, and we should continue adding hydrochloric acid and let the reaction proceed. So, after a few days, when we try to add more hydrochloric acid and we'll not see a single bubble of gas being released, that means it's time to filter the powder. This process dissolves almost all the zinc from our zinc-ruthenium alloy, leaving just the ruthenium powder. This washed precipitate is exactly what we need for today's experiment. I'll transfer it to a petri dish so I can show it to you up close in ultra macro detail. And now the ruthenium we got this way has a really fascinating property. It can actually explode when heated. Let's try heating a little of this powder and see what happens. To film this at a higher frame rate, I had to shrink the area captured by the high-speed camera, so I repeated the experiment in a test tube. In pure oxygen, this ruthenium ignites even more brightly and spectacularly, forming ruthenium dioxide. When heated in air, the hydrogen bound in ruthenium is released and reacts with atmospheric oxygen on the metal's surface. The sparks are made of tiny ruthenium particles that continue to release hydrogen, which oxidizes on the surface, with ruthenium acting as a catalyst, creating a glowing effect. Here I repeated the previous experiment, but used a larger amount of the substance, and instead of pure oxygen, I introduced ozonated oxygen into the flask. I was really curious to try this experiment in an oxygen-free environment, so I took a flask, added the ruthenium powder and filled it with argon. In this setup, hydrogen shouldn't oxidize on the ruthenium surface, but will it really behave that way? Let's see. Incredible! There was no oxygen in the flask, but we still saw a small bright glow on the surface of the ruthenium powder. How do you explain this? Write your thoughts in the comments, cause I think the ruthenium we get after removing the zinc still has some oxygen in it, because otherwise there'd be no way for the glowing hydrogen oxidation to happen. I still have some powder left to test an idea. It's interesting, we know that hydrogen reacts with chlorine in the light, but how will this powder behave when it comes into contact with gaseous chlorine? For this experiment, I'll just pour it into a test tube with chlorine and we'll see what happens. It's really interesting, the reaction with chlorine took place without any external heat, and we could barely see any sparks. Unlike chlorine, nothing happened right away in bromine vapors. I had to heat the ruthenium to get the reaction started. I also tried heating this metal powder in nitrogen dioxide, but it wasn't impressive. It acted just like it did in argon, and since the gas is pretty dark, we couldn't see any glow, though maybe there wasn't much glow at all. And of course, I wanted to test how resistant this platinum metal is to xenon difluoride. I added a few crystals of this noble gas compound to a test tube, and then put in some ruthenium powder. It turns out ruthenium isn't resistant to xenon difluoride at all. It gets fluorinated immediately upon contact. So guys, that's the interesting video about ruthenium, at least in my opinion. Of course, I hope I'll be able to synthesize ruthenium tetroxide and make a full video about this oxide. Thanks for all your likes and comments. And of course, a huge thank you to my patrons. Without your support, I wouldn't be able to make this kind of unique chemistry content. Thank you for staying with me for such a long time. Thanks for watching, see you in the next video.